We now look at what happens when I have an exponential multiplying by the function f of t and what that does to the Laplace transform. We saw earlier when we have a shift or a time delay in the function that results in an exponential times the Laplace transform of the original function. Now we can find out how we can create a shift in our Laplace transform as well by multiplying f of t by e to the ct. We can prove the following theorem, that when I take the Laplace transform of e to the ct of f of t for s greater than a plus c, what I can find is that this is the form that I'm going to get, that essentially the Laplace transform of this particular function causes, the exponential causes a shift inside of the function. And so that can be of help to us because it enables us to be able to find or recover functions that have been shifted. So we can prove this particular theorem by looking at the integral from 0 to infinity of e to the minus st times e to the ct f of t dt. And what we end up with is the integral from 0 to infinity of e to the minus s minus ct f of t dt. Now this doesn't quite look like the Laplace transform, but if we were to let, for example, k equal s minus c, and the integral does not depend on s or c, we can change the form so that it looks like the integral from 0 to infinity of e to the minus kt f of t dt. Well, s to begin with was some sort of dummy variable. The integral did not depend on it. This is going to yield a result that is going to be some function, in this case, of k. And so this is going to end up being the following. It will end up being f of k. But k is simply s minus c. And so we end up with the Laplace transform shifted by a value of c. And so that's what multiplying by the exponential does for us. Let's take a look at some examples in which we find the inverse Laplace transform. This function here, g of s is equal to 1 over s squared minus 4s plus 5, does not look to be one of the original Laplace transforms that I know. Furthermore, there is no way for me to split this up using partial fractions. So I'm going to have to do some form of completing the square in the denominator to make it look like a function that I can find the inverse Laplace transform of. We look for one that resembles some of the salient features. The salient features being the s squared, the numerator being a constant, and having some constant adding to the variable. The only one that remotely resembles this would be the Laplace transform of the sine of at, which we did at the beginning of this lecture, which is equal to a all over s squared plus a squared. So if we can transform our function g to make it look more like this, we should be able to apply the previous theorem and use the fact that there is some sort of a shift in the Laplace transform. So if I were to do this, what I'm going to do is the following. I'm going to separate s squared minus 4s plus 5, and what I want to do is I want to figure out what I can add to this in order to make it a perfect square. If I were to take 4 from 5 so that I get the following, s squared minus 4s plus 4 plus now 1, I find that this trinomial right here, if I were to group it, is indeed a perfect square. And so I now end up with 1 all over s minus 2, the quantity squared plus 1. This looks almost identical to our Laplace transform of sine, only where the s term is going to be shifted by 2. And so if we have a shift in the Laplace transform, this results in an exponential that multiplies the inverse Laplace of the function. So the function that I'm going to be considering is the inverse Laplace transform of 1 over s squared plus 1, which is most certainly going to be the sine of t. And since it's shifted by 2, the shift is going to give us the following. C is going to equal 2 in this case, which means that this is going to result in an exponential of e to the 2t. And so then using the previous formula here, I find the inverse Laplacian of f, which gives me sine, and then I use e to the ct in order to document the shift in my function. So that means that the inverse Laplace transform of g of s is therefore going to equal e to the 2t times the sine of t. In the next example, we're going to try to now put a lot of things together. In this particular example, we see that we have the presence of the exponential e to the minus s. This is going to indicate that we're going to end up with some type of Heaviside function. And in this particular case, also remember that when I have the following, when I have the e to the minus s times some function, the inverse Laplacian of this is going to equal u with the discontinuity point times the original function shifted by that discontinuity. This was the previous theorem that we had just used. So this right here is going to be the solution to our problem. We just need to find h. So following through with the strategy that we discussed in the previous examples, I'm going to go ahead and separate everything from the e to the minus s. And let's call this here h of s, which is going to be considered as the Laplacian of h of t, the Laplace transform of h of t. We want to find the inverse Laplace transform of h of s in order to recover h of t. And so in order to do that, I'm going to use partial fractions to split this up. I know that I can use partial fractions in this particular case because of the fact that I can factor the denominator. And so when I factor the denominator, I will end up with a all over s minus 1 plus b all over s minus 3. Multiplying through by the denominator, you'll get s minus 2 is equal to a times s minus 3 plus b times s minus 1, so that when a is equal to 1, when s is equal to 1, I will end up with negative 1 is equal to negative 2a, or 1/2 is equal to a. And that when s is equal to 3, I will end up with 1 is equal to 2b, so that 1/2 is equal to b. Combined, this now means that h of s is equal to 1/2 of s minus 1 plus 1/2 of s minus 3. And now we need to take a look at an inverse Laplacian that will give us 1 over s minus 1. Note the following, however, that the Laplace transform of 1 gave us 1 over s. And so if f of t is equal to 1, that will certainly give us the rational function that we desire. However, our terms are shifted by a particular value. And so using the previous theorem, we know that we're going to end up with e to the ct times the shift, where c is the shift. So c has to be the shift. In this case, the shift is 1, and in this case, the shift is 3. which means if I go to find my inverse Laplacian, this will be e to the t times now the inverse Laplace of 1 over s, which is just simply 1. If I were to shift this, sorry, I don't have to shift it, plus e to the 3t times the inverse Laplacian of 1, which is just of 1 over s, which is just simply 1. And so our function h of t is going to be e to the t plus e to the 3t, all times 1/2. And you can use this in your function h so that your final answer is going to be given by f of t is equal to u1 of t times ht minus 1, where ht is going to be given by the above function.